So, hi, thank you all for being here today to listen to our presentation. And the subject of this presentation is safety related to roundabouts, considering two different kinds of traffic flows, which are basically the traffic flows related to traditional vehicles with the normal driver and the vehicles that have no driver, so the autonomous vehicles. The study has been conducted by Alessandro, Severino, Giuseppina Pappalardo, and Salvatore Trubia. And the title is indeed Safety Evaluation of Two Roundabouts Considering Autonomous Vehicles Operation. Let's go ahead. I cannot go, yeah. So the way the study is structured is in three different parts. The first part considers the study of the CAVs, which is the connective autonomous vehicles, and the intelligent transport systems called ITS. The second part is the analysis of the more, let's say, the calibration and the validation of the models we have used to conduct this study. Specifically, we would say Wiedemann 74 and Wiedemann 99. The software we have used is VisSim. And the third part of the study is about the data analysis through a software called SAM, Safety Performance, and we will see this later on. Let's go ahead. So we can see that the European Commission has published some data on traffic and road accidents in Europe in the magazine Road Safety in the European Union, Trends and Statistics and Main Challenges in April 2018. Shortly, we can see that the trend describing the number of accidents through the years in the last, I would say, 15 years is decreasing, which is a good thing. However, we think that we can reduce furthermore this trend, this number of accidents. To do so, we have to focus on three different classes of technologies. What I mean is that we have to intervene to the accidents caused by vehicles against vehicles, so V2V, the accident between vehicles and infrastructure, so V2I, and finally the accidents related to vehicles against X, which means vehicles against pedestrians, bicycles, light mobility, and so on. This slide shows the 5 different levels to describe an autonomous vehicle. The level we want to consider in this study is the last level, level 5th, which is called in reality level 4B. It means that a CAV, so an autonomous vehicle, is characterized by being connected with a network, cooperating with other similar vehicles, so there is an interaction with other vehicles. And finally, there is no physical driver, so the vehicle is indeed automatic. There is no human being driving the vehicle. And we have a nice slide here with some photos. So as you can see, it's quite modern as a technology. In this slide, we can see the typical geometry we have considered in this study, speaking of roundabouts. Also, there is an example of an origin-destination matrix, which you can see here. And again, so we have used some behavioral models, 2 of them. The model Wiedemann 74 has been used to describe the behavior of classical cars or traditional cars, if we want, whereas the model Wiedemann 99 has been used to describe the behavior of autonomous vehicles, which we have called CAVs. This chart is actually a description of the behavior of these vehicles in general, and we can see that depending on the difference of velocity, we have different distances of safety in case we want to brake, for example, or we want to stay in queue in line with another car. Right, let's go ahead. Hang on. So, and okay, the software we have used to analyze these behavioral models, it's Vissim. Now, speaking on the model Wiedemann 74, so this is the model we have used to describe the behavior of classic vehicles with a human driver inside. And we have, of course, some parameters inside the model. We have some values which are default and other values that are calibrated by us. And this table here summarizes all the parameters, some of the parameters we have used in this model. You can see that along the ring, the trajectories of vehicles develop inside. The ring is, of course, the ring in a roundabout. And along all the arms of the roundabout, the trajectories of the vehicles are randomly defined within the lane. That's because there is a human driver inside the car. This slide is related to the other model we have used. So it's Wiedemann 99, and it describes the behavior of the autonomous vehicles. You can see all the parameters we have used with the calibration of this model. So they range from CC0 to CC9. They're described here. I think it's probably quicker to go ahead, but each parameter has been described. So we have standstill distance, headway time, following variation, threshold for entering, following thresholds, speed dependency of oscillation, acceleration, and standstill acceleration, and acceleration at 80 kilometers an hour. Again, we have another description of these parameters. The main difference here is we have highlighted in yellow all the parameters we can find in the existing literature, whereas the ones that have not been highlighted in yellow, they actually have been set up from us. And again, we have a default value and a calibrated value. Below, you can find the literature that we have used to get these highlighted parameters. And again, we have another table with a further description of these parameters used in Wiedemann 99. Sorry. Now, the video you're looking at is actually a description, it's actually showing the behavior of the vehicles who had driven by a human driver. So this is a classic vehicle, not automatic, and you can see here in this circle how the vehicles behave in this situation. On the right, you have all the graphs, the charts, and give you more technical details. I think this has been done in Japan, is it? Japan. Whereas in the next slide, right, this one instead is a simulation of what happens when we have where we have autonomous vehicles and using the Wiedemann 99 model with the parameters we have adopted in this model. So this is what happened, and we can see that there is a constant distance between each vehicle, whereas in the other slide, the one we've seen before, we can see it is a bit different. So these cars are driven by humans, and the distance will be different. As you see, there's a lag, there's a delay. It's not uniform, I would say. Whereas if we analyze, if we analyze the automatic vehicles, we see that their motion is uniform. So the distance between vehicles doesn't vary. And let's go ahead. Come on, yeah. Now, we are now at the final part of the study, the third part, which is the data analysis through the software we have called SAM, It stands for Surrogate Safety Assessment Model. We have a nice chart here that says that depending on the time to collision and the conflicting speed, we have different levels of severity of the accident. We can say that if we have a high time to collision and a high conflicting speed, the severity of the accident is higher than in the other situations, I would say. So we can enter with this couple of data here. We can go through this line here, this curve here, and we can assess the severity of conflicts. And as you see, we have two areas of the chart where we have serious conflicts and not serious or less serious conflicts. These has been obtained by data analysis with the software SAM. We have another chart, again from SAM. What we see is that if we reduce the percentage of vehicles in the traffic flow, of autonomous vehicles in the traffic flow up to 0, we can reduce of 90% the number of potential conflicts every 1,000 vehicles. This means that
2 minutes left.
Yes, I'm done, really. And again, if we want to reduce even further this number of potential conflicts, we think we can intervene by changing the road geometry and also the way the information exchanged by the geometry and the vehicles when they drive, automatic vehicles, we're speaking. And that's pretty much everything. I read the conclusion. And so the discussion explained within this article has been shown several times how road intersections must be considered as crucial parts of the road network. Therefore, they represent the critical areas where vehicle trajectory conflicts can take place. Hence, poorly designed intersections can easily lead to congestion phenomena with the consequent formation of vehicle queues, and in several cases, even to serious or very serious accidents. Therefore, the right choice of intersection layouts, such as turbo roundabouts, becomes fundamental to offer a better level of service to users, giving them the opportunity to travel in the shortest time possible on the routes of the road they have chosen. The method of this article concerns the use of simulations of the road environment through the application of vSim software, and then the use of simulation of potential traffic conflicts through the application of SAM software, which respectively reproduce the behavior of the vehicles inside a turbo roundabout. Thank you very much for your attention, and goodbye.